Hi everyone. In this video, I want to continue looking at applications of exponential functions. So in this one, I'm going to give you the equation and I want to see if we can figure out what is happening in the context of this problem. So this problem is Beth has a garden. She's purchased ladybugs to release into her garden to help eat aphids. She's got an aphid problem. We're going to have L be the number of ladybugs, and A is the number of aphids, and T is the number of months since she released the ladybug. So we've got our variables, and we just want to look at each of these equations and decide what's growth, what's decay, how much is it increasing by or decreasing by, how much did we start with, how many ladybugs were there initially or aphids initially. Okay, so let's see. I'm actually going to block off so we can look at one at a time. So the first one, and I think I said this in an earlier video, I really like to compare and contrast a little bit with linear functions because there are some similarities. With linear functions, we have this y equals mx plus b form. And this one lets us immediately see how steep our graph is and what its y-intercept is. So just from looking at that y equals mx plus b, we can figure out roughly what our graph looks like and have a good idea of what's happening to our y values. With exponential functions, we have this y equals ab to the x. And in that one, we also get a y-intercept from a. And then we have the base of the function. So instead of slope, where we would go over 1 and then add 2 to our y, over 1 and add 2 to our y forever, we would have something like we go over 1 and we double our y. We go over 1 and we double our y again. So they're similar, but absolutely not the same thing. And we want to be really careful that we don't forget how linear works just because we're looking at exponential. So the first one is linear. We have a slope of 25 and the y-coordinate of our y-intercept is 30. So in this case, if we're thinking about number of ladybugs as a function of time, this tells me I'm starting at 30 and then I have this over 1 up 25 thing happening. So if I want to describe what's happening to the ladybug population, this is definitely telling me about ladybugs. I would say she released 30 ladybugs and there are 25 more ladybugs each month. So let's say Beth released 30 ladybugs and there are 25 more per month. Okay, so this is what's going on. This is a linear relationship. In linear relationships, you would add or subtract the same thing over and over. So we start at 30, and then every time t increases by 1, we add 25 to the number of ladybugs. Second one, this is an a of t function, so this is going to be number of aphids. So in this one, it's definitely exponential, which means I'm looking for a repeated multiplication type model instead of a repeated addition or subtraction. So here, if you ever get stuck, remember you can always plug in numbers. If I plug in t equals 0, 1/2 to the 0 is just 1. So I'm getting 220, which means I'm starting with 220 aphids in the garden. I'm then multiplying that by 1/2 over and over again. So when t equals 1, I have 220 times 1/2, half of what I started with. When t equals 2, I have 220 times 1/4, 1/2 squared, so 1/4 of what I start with. When t equals 3, I have 220 times 1/8, an eighth of what I started with, so it's cutting in half over and over and over again. Every time we increase t by 1, we're multiplying by another half. So this is going to give us that nice exponential decay shape. And I would say there were initially 220 aphids. And this was cut in half every month. Okay, so starting with 220 aphids, we're going to multiply by 1/2 over and over and over again. Every single month we'll multiply by 1/2. So again, with linear functions, you get the initial amount here. With exponential functions, you get the initial amount out in front. And if you ever forget this, you don't have to memorize it even. Just remember that if you want an initial amount, you're plugging in 0 for t. So it'll wipe out the 25t in the first equation, and the 1/2 to the t will become a 1, and that will disappear from the second equation. The slope of the linear equation tells me that I need to add 25 every time t increases, whereas the base of the exponential function tells me I need to multiply by 1/2 for every time the t value increases. Okay, next one is another L of t. So this one is telling us about ladybugs. And this is not meant to be all these things are happening at once. This is another possible scenario. So in this one, it's definitely exponential. I can tell because t is in the exponent. So I'm looking at an initial amount out in front. That's the y-coordinate of my y-intercept. So she initially released 25 ladybugs. I'm going to start writing an abbreviated version here. Release 25 ladybugs. And then the 1.5 is saying every time t goes up by 1, I multiply by 1.5. So I'm getting half again as many ladybugs. I think the easiest way to say that is that the number of ladybugs are increasing by 150% per, what was this one, month. Okay, so if you're multiplying by a decimal, generally the easy way to deal with that is to think about it as a percent. If you multiply something by 1.5, you have all of what you started with plus 50% more. So it's, oh, I'm sorry, not increasing by 150%. It's increasing by 50% each month. Okay. Next one, a of t is equal to 360 minus 20t. The 360 is going to be the y-coordinate of our y-intercept. Even though this is written in the opposite order, it doesn't matter. The constant is always the y-coordinate of your y-intercept. So that's our plus b. So this is initially, there were 360 aphids. The minus 20t is telling me that that number is going to decrease by 20 every month. So again, a linear relationship here. This is a decreasing linear function. There were initially 360 aphids that decreased by 20 each month. Okay, getting into slightly trickier exponential. This 2 in the exponent is something really important to be aware of. It gives us a lot of flexibility. What that does basically is adjust how often the base is being applied. So in this function, it's an L of t, so this is ladybugs. So Beth released, if I can spell released, there we go, 60 ladybugs. And this multiplying by 1.2 is saying we will have all of what we started with in an additional 12%. So this is telling me that it's increasing by 12%. And then the 2t is really important. So this is going to adjust how often that happens. And I would say, again, if you get stuck and you're not sure whether it's happening twice as often or half as often, that's the easy confusion, you can go ahead and just try some t values. So for example, now if I plug in t equals 1, that means 1 month has passed. And after 1 month, I'm multiplying the 60 by 1.12 squared. So they've already gotten their 12% increase twice at the end of a month. So I would say increasing by 12% 2 times each month. So basically, if you multiply your t by a 2, it's speeding it up. If you're thinking about graphs, this is a horizontal compression. So you're going to hit those same number of ladybugs twice as fast. You're going to get there sooner. You're going to get the same y output with half as big of a t input. Again, anytime you get stuck on that, just plug in some t values and see if you can figure out what's happening. Okay, last one here is another a of t. So this is number of aphids. It is exponential, so this number out in front is my initial amount. So initially 850 aphids. And then we're multiplying by a 0.6, which means it's decreasing. This is definitely decay. The previous one was growth, and this is definitely decay. Anytime you multiply something between 0 and multiply by something between 0 and 1, it's going to shrink, so that'll give you exponential decay. If we're multiplying something by 0.6, that means we're ending up with 60% of what we started with. Again, I think the easy way to explain that is to use the words percent increase, decrease. So I would say it's decreasing by 40%. If we were multiplying by 1, that would be 100% of what we started with. If we're multiplying by 0.6, that's 60% of what we started with, which means it has decreased by 40%. And then again, if you have any trouble trying to decide if this 3 is 3 times a month or every 3 months, that's usually the confusion, feel free to pick some t values. This one, when I look at it, I see that if I plug in t equals 3, that means 3 months have passed, and I'll end up with 850 times 0.6 to the 1. So in 3 months, we've multiplied by 0.6 once. We've gotten the 40% decrease once. Decreasing by 40% every 3 months. And this, in terms of transformations, is a horizontal stretch. So it's going to take longer. It's slowing you down. It's going to take longer to get the same a value from this function than if there were no divided by 3. All right, thanks for watching.